Welcome to Lecture 6 of Introduction to Robotics. And so our big goal is being able to describe how, if we change the position of some of the joints, how that affects the position and orientation of the final joint, the gripper that we have here. And to do that, we're going to use something called the de Navant-Hardenberg convention. And we're going to do a number of examples today. And these examples are because next lecture, we're going to go into inverse kinematics. And before we can appreciate that process, we need to understand a number of different robot models and how these joint transformations affect what happens at the end effector. On this picture is a picture of the UR5, the Universal Robotics 5, which is a 6-joint robot. And what we'd like is to have a system where all roboticists can talk about what happens to the end effector if we rotate the base by 5 degrees and the wrist by 5 degrees. To do this, we're going to use some conventions, and conventions matter. I know we just came from the Democratic and the Republican conventions, but when we're talking about conventions, we're talking about the mathematical rules that we use to describe the process we're following. Here is a comic from a famous example of when two parties use different conventions. You see, for the Mars Climate Orbiter, this beautiful picture here shows it as it's being tested. The entire thing costs about $330 million to send to Mars, and it actually made it all the way to Mars. And while it was doing its orbital insertion, something went wrong and it crashed and burned up in the Martian atmosphere. And when they looked at it, they found that actually Lockheed Martin had been providing thrust in units of foot-pounds, so imperial units, whereas NASA was expecting units in terms of SI and newtons. And so that mismatch, about 4.45, caused the whole thing to destroy itself. And so our goal today is to go through a number of different robot examples so we can follow the same process and arrive at the same answer as others. Let's jump in now. So here's our first problem, and this is one that we gave you for the practice for this lecture, but let's go through the answer. So the first thing that we need to do when we're given a robot like this, we'll see that it is a revolute and then prismatic arm. The first thing we need to do is put in our z-axes. So we put them, the revolute one is coming right out of this revolute joint, and the prismatic one is translating along this joint. And so I know that this is going to be my second. So this is z0, and z1 is translating along this. Right. Now the first thing I need to do is to put in my base frame, and to do that I've got to conveniently pick out, well, I need to first pick out an origin. Makes sense to put it in the same plane as everything else. And then I need to add my x-axis. So I'm going to put my x-axis coming right over here. This is x0. All right. The next thing I need to do is identify my next x-axis. And so remember, what I do is I find the common normal between my two z values, between my two z-axes. So z0 is coming out of the page, and z1 is here, translated there. So the shortest distance between them is going to be right along this line here. And so I follow this line up here. The intersection right here is going to be my origin. That's O1. And then if I continue on from there, then I get my x1 value. So there's my x1 value. And then I am going to march along this axis, and I've already got my origin for my end effector, z2 and my x2 here. So now it's time to fill out this. I guess I could stop here for a bit and add in my other axes. So that means that my y0 is coming here. And then to make a right-handed frame, my x, I'm going to have my y1 coming out of the page. And that means that this y1 is also out of the page. So now it's time to fill in my DH table, and this says link 1 and link 2, and then I need to add my values. So let's start with my first link. So the distance that I move along my x1 value from my previous origin to my next origin, along that common normal, that is my R1 value. So I'm going to label that here as R1. The link twist is how much I have to twist around my X1. So I'm going to put my thumb in the direction of X1, and I'm going to point outwards to my Z1, and then I'm going to rotate that around. So remember, our angle twist, we measure with a thumb along the X1 axis, and then we point outwards along our Z0 axis, and then we're going to rotate that over until we're pointing to the Z1. That's my positive rotation. That value there is going to be my alpha 1. And so my alpha 1, you can see that's 90 degrees, so we'll say that's pi over 2. We've got that. My d value is the distance we travel along Z1. Everything's in the plane there, so that's going to be a 0. And then theta I is my angle. I'm going to do that in green. My angle from my x0 to my x1 along my z0 axis. So that is my theta 1, and that is my variable. So theta 1 is my variable. I've got that there. Next, I need to do my second link. And so the first thing I look at is, well, I'm moving from this origin, O1, to this origin, O2. You can see that everything is aligned. We've just got this distance that we're translating. We're translating this distance along my Z1 axis. So that is going to be a D2 value, and that is my variable because it can change. You notice my X1 and my X2 are aligned, so there's going to be no twist. So my alpha is 0. I've got my D2 star value. You'll also notice that since my x's are aligned, I've got 0 theta. There's no twist around that Z2. And finally, my R value, since there's no travel along my X2 value, that's also going to be 0. And so now what we need to do is go through here and build my A matrices. So I'm going to start with my A1. A1 is equal to, and as we build this out, A1, remember I've got the values right over here for what that is. And so this is going to be mostly a theta 1, but I've also got an alpha value. So my cosine of pi over 2 is going to be 0. So this second column is going to be zeros. So I can write that in as 0, 0. And then I've got a 1 because sine of alpha of pi over 2 is 1. So I just get my cosine theta, my sine. So in my notation, we just write that as C subscript 1 as the cosine of theta 1, sine subscript 1 for theta 1, and a 0. My sine is of alpha is 1, and so I just get sine of 1, cosine of 1, 0. Remember, the bottom row is always going to be 0, 0, 0, 1. And then my offset here is going to be determined by my radial distance that I've moved, because I got 0d. And so it's just going to be R1 C1 and R1 sine 1. Now let's go ahead and let's make, so that was 1 A2. A2 is equal to, here we've got a much simpler matrix. He's only got a D2 value, so it's just going to be an identity matrix in the top here. So we got a 1, 1, 1, 0, 0, 0, 0, 0, 0. Bottom row is always 0, 0, 0, 1. And then the only term I have is my D2 star. So I got a D2 star right here, 0, 0. So my total transformation, what is T2 in frame 0? That's equal to A1 times A2. So we can work that out right now. I'm going to take this first row here and multiply it through, and I get a cosine 1. Nothing for this next time term. It's actually, we just are going to get the identity matrix, the first one, so I can just copy that down. Our bottom row is always going to be 0, 0, 1. We're not going to get the identity matrix for this next column, but we can work that out. So my first column multiplied through, I've got an S1 D2 star. I'm going to need a little bit more room here. And then I am plus my R1 C1, because that's multiplied by this one down here. Then my next term here, through here, I'm going to have my C1 is going to multiply here, so C1 D2 star. And I have forgotten a minus sign, so that's going to be a minus there. A minus C1 D2 star plus R1 sine 1. And then we've got D2 and we've got a 0 here and a 1 there, and that finishes our total transformation. So let's do a little bit of thinking about what's going on here. So the first thing that we're going to look at is this first column. This first column tells us which direction is my x2 facing. So you can see this x2 is totally dependent on my rotation of theta 1. And so if theta 1 is 0, then the x2 is going to be pointed in this direction. And as it rotates up, it moves. My next column says that my y1 is just going to be pointed in the direction of z0, which it is. It's the same direction here. And then this final column here, this is showing which direction my z2 is pointed. You can see that it's just sine 1. And again, I've missed my negative sign here. So let's go write that in. Negative sine 1. Negative cosine 1. And so we've got our rotation there for that. And then this final term tells me what is the position of this origin. And so you see it's determined by two things. We've got our first, this term here is the length of this D2, plus I've got my radial offset here. And then I've got a negative cosine of my D2 star, and then my R1 sine 1, which tells me this position. Now if we look at another drawing, and this is the drawing that we're going to look at in Mathematica. You see we've got our Z0 coming out here, but we've got our Z2 pointed here. We've got our Z1 pointed here, and our Z2 is parallel with that. So let's look at that in Mathematica. Let's do my first example is this RP arm. So in Robotica, we just need to set the notebook directory and then load it. And then we load in the DH parameters that we've seen here. So I'm going to run this over here. You'll see that I get the same DH table that I was expecting. Over here, I'm plotting out what is my total transformation. So you see the nice thing about Robotica is that it simplifies your math out quite a bit. And that helps because these rotation matrices are going to make a complicated transformation matrix. And then over here we can see our robot. Let me give it a little bit of a D2 value. And let's look at it from the side just like we saw it in our demonstration. You can see that the lines that we've drawn between the joints look a little bit different than the drawing, but these are just showing how that fits together. So I can rotate this around. As I do my positive rotation, it's going to the left. Go negative, it turns to the right. And then I can extend that last frame out and in. Sometimes it's easier to see that with all of the vector arrows drawn on here. So here we can see that with the vector arrows drawn in as we rotate around here. So if we start in the default position, our x-axes line up. The drawing that we were given, we had already rotated a little past, and so this looks a little bit more like the drawing we were given. And so you can see that this angle that we moved here, that is our theta 1 angle that we have. Here we've got our elbow manipulator. So this is an RRR robot. So let's go ahead and let's draw our axes on it. This axis right here, that's going to be my Z0. Coming out here is going to be my Z1. My Z2, which is parallel to it. I just am a terrible drawer. And then over here we've got our Z3 axis coming out. And here we've got our x3 coming out, which means that this direction here is going to be my z3. And so now we're ready to write in all of the DH parameters. Let's go ahead and let's draw some of these in here that we can see. We've got to first put our base frame in. So here's my base frame coming out here. I'm going to put my origin here. I'm going to put my x0 coming out this direction. And I'm going to drop this value down here. That'll help me out. I'm going to extend. And so just for my first one, remember that I'm going to write in my links 1, 2, and 3. For the link 1, my radial distance, well, let's just so now let's draw in I've got my Z1 here, and I want to find my origin for my Z1 frame. And so I've got my Z0 coming over here and my Z1 coming in here. They intersect at some point, and that intersection has to be my origin, O1. And then what I do is I extend that line. Now my x1 has to be perpendicular to both Z0 and Z1. Since they intersected at that point, I only have two options. Either because it's got to be perpendicular to each, I can either come out this way, or I could go into the page. I'm going to pick to come out this way and call that one my x1 value. So now I've got these two axes, Z2 and Z1, that are parallel. Because they are parallel, I can actually put my origin for for O2 to be anywhere along this line here. But if I put it right here, then I'm going to have 0D offset. And so that's going to simplify. I like that. So I'm going to say that's going to be O2. And then I have to make a line coming from there. I'm going to do that just to show that a little bit better. I'm coming from this origin through here and extending it outwards. That is going to be my x2 value. It'd be nice if I made that blue. So I'm going to make that value x2 in blue. And the similar thing for here. I've got my origin here. So continuing from this Z2 all the way out here, that's why my x3 is pointing out this way. Now I can go back through here and just add by the right-hand rule where my y are going to be. And so my y0 is pointed out here, 90 degrees there. And then I've got my x1 and my z2, so I'm going to have a y1 there, y1 there, and I've already got my a y2 there, and I've got my y3 already. So now let's draw in the values, the non-zero DH values that I have in here. And so I am moving along my Z0 axis up to here. So that is a distance that I'm moving along the Z axis. That is going to be my D1 value. And it's a constant because that's built into the system. Now over here, I am moving along my X2 value. So this right here is going to be my R1. I misspoke, my R2. That is also a constant. This distance over here is what I'm moving along my X3. And so that is going to be my R3 value there. Those are non-zero values that I have. I'm also going to have to look and see if I have any alpha twists. And I just need to look for consecutive z-axes that are not aligned. And so I can see right here, if I translate this z1 up to here, z1 translated, and if I put my thumb along this direction, along my x1 direction, in order to align my z1s, I'm going to have to, my z0 to my z1, I have to rotate it 90 degrees this way. And so that is going to be a alpha 1 is equal to 90 degrees. And so now I have everything that is non-zero in here. And so I can write those in. So I've got a 0 radial offset for this one, but I do have a twist. That's 90 degrees there. I have a D1 value that I've offset. And I have my theta 1 is going to be my distance that I rotate around Z0. That is theta 1. That's a variable. So that is my theta 1 star. Let's go ahead and let's write in those other rotations that I have here. And so this rotation that I do about z1 from x1 to x2, that is my theta 2 star. And over here I did a rotation about my z2 from x2 all the way over here to x3. That value there is going to be my theta 3 star. I can go ahead and write those in. And then I've got my R2 and my R3 and 0, 0, 0, 0. Now I have everything that I need to write this in, and I can go ahead and write those. So I've got my A1 is equal to, I've got my C1, S1. This is the same thing that we had in the previous page. Negative C1 though. It's important to have that sign in there correctly. And then the only offset that I have for this one is my D1 value. My A2 is also something that we've seen before. Here, since I've got no alpha twist, everything's in the top left corner. So I got a C2, S2, negative sine 2, cosine theta 2, and 0, 0, 1, 0, 0. My bottom row is going to be 0, 0, 0, 1. And then I've got a radial offset, so R2 cosine 2, and my radial 2 sine 2, and a 0. My A3 looks exactly the same, except I just replace all those with 3's. So I get a C3, S3, 0, 0. And I get a negative sine 3, cosine theta 3, 0, 0, 0, 0, 1, 0. And then an R3 cosine theta 3, and an R3 sine theta 3, a 0, and a 1. Now I'm going to take all these things and I'm going to multiply them out to get my total transformation. 3 in frame 0, well, that's equal to A1, A2, A3. And that, I am not going to force you to watch me do that because I'd make mistakes. But I'm going to write this out here, because you can see that it has gotten somewhat complicated. So let's look and see if we can understand a few things that are going on. So let's look at this simple one right over here. This says that the direction of my final z-axis, which if we look at it, you'll see that that is pointing out this page. That's always going to be just dependent on what my theta 1 value is. It's the only one that can really change which direction that is, whereas that theta 1 is going to apply to everybody over here. Whereas all these terms are just a summation of these 2 and 3. In fact, you'll never see theta 2 by itself. And the reason for that is because these axes are aligned, and they'll never not be aligned. There's nothing in between to interrupt that. You can look at, we can now control our position in x, y, and z. So you notice this, the x value here, the y value here, and the z value here. D1 is the only one that can affect our z value. And that's all it affects. It's not a variable though. Where these terms over here are something that we've seen before when we worked out by hand. And this is very similar to what you're going to have for your OWI robot. All right, so let's look and see what that looks like in Mathematica. And so the first thing I do is I set my notebook directory and I load Mathematica, and then I give it the DH parameters that we just worked out. So if I run that through, it's going to say, oh, here's my table of parameters. That's just what we worked out there. Next, if I call forward kinematics, it's going to compute my A matrices and my T matrices, and then I can simplify that trig notation. And I will get these three A matrices that we expected to see. Next, if I want to see what does that total transformation t look like? Let me just run that out here. And that's what we had as well. And that's actually how I wrote out what we had. And then we can plot it. And so in order to plot it, I have to tell myself, give some values for R2 and R3, because those I left unsolved here. So we'll set them both to 1. And then we can build that out, either showing just a point over here, or we could go ahead and we could say, I want to show that, well, I want to show what all my arrows look like. And so let's see this one with all the arrows on here. And so this is our RR manipulator. You can see we can rotate a positive or a clockwise value over here, rotates my arm around. And then you notice that in this default position, with theta equals 0, everybody's aligned with the previous x-axis. Here I can rotate it past there and rotate it here. You can see all of our coordinate frames as they move around in that. Now it's time for our RPR arm. And so we've got our z-axis of rotation. I'm going to put in my z0 there. This one here is going to be my z2. And this axis that I'm moving along here, that's going to be my z3. So first I have to put my origin in there. And so I'm going to put all those in the plane. So here is x0 coming out there, which means I'd have to put my y0 in this direction. Now where is, and I've already misread, this should be my z1. And so I've got my z1 moving over here. The intersection is going to be right at this point here. And so the intersection means that my x1 has to be perpendicular to both my z0 coming out of the page and my z1. And so I've got two options for that. I'm going to pick it coming vertical, although I mean I could go this direction, but I'm not going to do that. This will be my x1 value coming out there. In order to get a right-handed frame then, my y is also going to be, my y1 is going to be parallel with my z0. So now we've got my z2 coming out here, so that these also intersects. This intersects with my z1. And so to be perpendicular to that, I can pick either up or down. Let's pick up. So this is going to be x2. My y2 was going to come out in this direction. And then I've got my final spot, which was given for me. And so I've got my x3 coming out this direction. And so now we need to identify all the non-zero values that we have here. Well, it's obvious that I've got a distance from here to here that I'm moving, and that is going to be my d2 star. It's my only d2 since everything else is in the plane. Next, I have to have my theta value, which is my rotation around my z0 from x0 to x1. That is my theta 1 star. And then I also have a theta 3 star here. And now we need to think about my alpha values. So my alpha is the twist about my x1 to go from z0 to z1. And that value here, I'm doing a rotation of 90 degrees for my alpha 1. Now over here I've got my z2 is coming out this direction. This is my z2. And I need it, my z1. And I need it to point along the z2 by doing a rotation. And so that's going to be a rotation of negative 90 degrees. And now I've got all the values that I need, so I fill out my DH table, 1, 2, 3. My R1's values I had as 0 and 0, and I lied. There's also this value that I have, this offset here, and that is along my x3 values. That is my R3. So R3 value there. I've got a 90 degrees from first alpha, a negative 90 degrees from next alpha, then nothing here. And then my d values, I got a 0, a d2 star, and a 0. And finally, a theta 1 star, a 0, and a theta 3 star. And so I can go ahead and I can write my a values. My A1 matrix, this is what we've seen a couple times already. We've got a cosine of theta 1, sine of theta 1, 0, then a 0, 0, 1, and then a sine of 1, negative cosine of 1, 0, 0, 0, 0, 1, and followed by 0, 0, 0, because I have neither D nor R there. My A2 value is going to be my distance that I move along, and so I do have a alpha in here, and that's going to twist my values here, so I get, one of the things you can remember is that our y2 here is pointing in the opposite direction that we had before. So that's why we're going to get a 0, 0, negative 1, 0, 1, 0, and then we get our d2 value here, 0, 0, d2 star. And then our A3 value, just a rotation here. And so this is our value that we've seen again several times. Cosine of theta 3, sine of theta 3, 0, 0. And then negative sine of theta 3, cosine of theta 3, 0, 0. And then 0, 0, 1, 0. And then R3 cosine 3, R3 sine 3, 0, 1. To get my total transformation, that's going to be my, well, I can write that. My total transformation, T, 3, and 0, is equal to A1, A2, A3, which I'm going to be able to squeeze in here. Let's look at the simplest column here. That is going to my z direction. My z direction is going to point out the same direction as my initial z direction. That remains unchanged. Whereas over here you can see that it's only the combination of the sum of theta 1 plus theta 2. Just to remind ourselves, C13 is equal to the cosine theta 1 plus theta 3. So it's just a summation of those two, because that's all, it's just the summation of those two tells you how much our final x-axis is rotated and how much our final y-axis is rotated. And then this position that we have right here is given by a d2 distance and then my r3 distance that I move outwards, where my r3 is rotated by both theta 1 and theta 3. So you can see how these all come in, and then my s1 is rotating my d2. And so you can see how those work together. Let's see that in Mathematica. All right, the RPR. So again, I've loaded these exact DH parameters that we had before in there. And then I run the DH input on that and grab the forward kinematics after I've simplified them. And I'm going to first show you what these A matrices look like and then the total transformation, and then plot it out. So you can see that these are exactly the answers I had here. This is how I get this transformation. You could do it by hand. That'd be fair. And then finally here is the robot, where you can see the frames. I'm going to tilt it on its side since this is a planar example. And so we've got, let's start with a non-zero D2. But we can rotate around our first joint, and that rotation moves our x1, our x0 and x1. So there's that theta 1 between them. Then I can extend outwards, or if I want, or I can bring it back in. Then I've got my third degree of freedom, which rotates from aligning my x-axis, and as I grow that, I'm rotating clockwise around.